Hi and welcome to Computer Science 312 practice lecture on the videos. So we're going to do some screen captures. I'm going to see if this works for next Wednesday and Friday if there's a bus strike. So far we've been going to continue on lecture from last Friday. And before this we've been talking about classes and individuals. And now we're going to talk about properties. So property just relates an individual and a value. So if we have RDF IPV, then P is a property. It's not just the middle part of any of these property statements, of any of these triples we've been using, is called the property. So the domain of a property is the class of individuals that can be in the head of the triple with that property. So if we have RDF IPD, then I must be in the domain of property P. So that's what that says. RDF of IPV implies I must be in the domain of property P. And so in Prolog, we can write exactly the same statement that says that if P has domain T, we're going to use the standard naming of RDFS colon domain, and that's going to be a standard meaning for domain that relates RDFS as a property that denotes property and its domain. So T here has a class, and if I is in the first argument of an RDF statement, then it must be the case that the type I has to be of class T, because T is the domain of P. Okay. So here's an example of doing that. If we have a property called lives in, and its domain is a person, if we observe RDF P123 lives in B52, this implies that P123 is a person. So in other words, and we write this as RDFS lives in RDFS domain person. So here we just use this particular property that relates lives into person, so we can actually imply that P123 is a person. Similar to domains, we have ranges. The range of a property is a class of individuals that can be in the tail of a triple with that property. So in other words, RDF IPV implies P is in the range of property P. V is in the range of property P. And again, we can write this in terms of triples. And again, we're like we did before, RDFS range is the standard meaning for the range property that denotes a property and a class. And now if we have P has range T, and V is a value, it's the third argument of using property P, then V must have type T. Okay, so it just relates that. Again, the range of lives in can be a place of residence. So in here, we're going to type down RDF lives in RDFS range, place of residence, means if you use the third argument of a lives in, you must be a place of residence. All right. So there are two different sorts of properties, fundamental sorts of properties in OWL. An object property is a property's range as an individual, and a data type property is one whose range isn't an individual. In particular, they're numbers or strings. So for example, mother is an object property. It relates to two people. Lives in is an object property because the range of it is a place of residence. A data type property is like name, schema.org/name is a data type property. Its range is a string. The height in centimeters of people might be a property, and its range would be a number, so it's a data type property. You could also have property inheritance. We could talk about subproperty of lives in. So lives in should be a subproperty of an enclosure. So if X lives in Y, then X is enclosure Y is true. Principal residence could be a subproperty of lives in. So then we have, if X is the principal residence has principal residence Y, then X lives in Y. So you live in your principal residence. Okay, we're typically going to share knowledge. So part of the semantic web is to do knowledge sharing. So one ontology typically imports and builds on other ontologies. So they're all building on top of each other. So lots of ontologies, we build and import other ontologies. So when we talk about an ontology, we typically mean an ontology plus all the things that's defined in that ontology plus all the things that it imports. And ALP also provides facilities for version control. It's important because you have to work out which ontology you're referring to at each time. And there are lots of tools for mapping ontologies into another, and they allow for interoperation of differently developed knowledge bases. So different knowledge bases can be interoperate if they map one ontology into another. And so finally, the semantic web promises to allow these pieces of information, two websites, two knowledge bases, to interoperate and can be combined if they both adhere to an ontology, so both of them have their meaning specified, and these are either the same ontology or there's a mapping between them. So you either have to share the vocabulary, or there needs to be a translation between those vocabularies for them to interoperate. It's almost always better to use an existing ontology than to define a new one. So it's almost better to try and see, is there a standard for this? And if there's a standard, use it, rather than defining your own new terminology. So if some particular ontology defines the term you want, import that ontology and then use it. And then other people who use that ontology can know what it means and can interoperate with others. Otherwise, you'll need to build mappings between your meaning of symbols and someone else's meaning of symbols in order to be able to share that knowledge. Turns out that ontologies have a long history, and so Aristotle in about 350 BC defined this idea of way to define ontologies. And now people often think of class hierarchies as trees, but they don't have to be trees. And so in fact, the definition of ontology that Aristotle suggested was much more general and doesn't usually end up in terms of trees. So he suggested that defining a class C in terms of the genus, which is just a superclass. So for each class, you define what a superclass is, and then the differentia, the attributes, where an attribute is a property and value pair that makes members of the class C different from other members of the superclass. And here's an interesting quote. If genera, where genera is the plural of genus, are different in coordinate, what he means here, coordinate means neither, one is not subordinate or superordinate to the other. So one's not a subclass of the other. The differentiator are themselves different in kind, which means typically different in kind. Take, for instance, the genus animal and the genus knowledge. So he's thinking of animals being a class and also knowledge being a class. With feet, two-footed, winged, aquatic, a differentia of animals. The species of knowledge are not distinguished by the same differentia. So in other words, we can distinguish one class of animal from another class of animals by whether they have feet or not, whether they have 2 feet, whether they're winged. But if we have classes of knowledge, they're not, you can't distinguish them by these. A two-footed knowledge doesn't make sense. Or as Aristotle says, one species of knowledge does not differ from another in being two-footed. So this Aristotelian definition turns out to be a good way to think about defining ontologies and typically doesn't end up in trees. I think we have trees are common because of biological evolution produced a tree, but for nearly everything else we don't have a tree. So instead of thinking about if we want to define ontology, start thinking about what classes to do, and then talking about what's the superclass, how does this class differentiate from that superclass. And then you can start a big game of how to actually go about building ontologies, and you can start building ontologies. Okay, let's stop here, and please send me comments about whether this works, whether you have other suggestions about how to do that, or how I could actually improve doing this. Okay, thank you.